So remember, the purpose of Chapter 13 in combustion, the objective is to come up with a process where you can transfer high temperature heat from one place to another. And in many cases, if you think about your steam power plant chapter, you think about your air standard cycles chapter, both internal combustion and then also the gas turbine engine model. You're looking for sources of heat transfer to accomplish the objective of making net power. And so in this coming up module for Chapter 13, what I want to do is talk about heat release. And one thing that I think I failed to do in the previous modules of Chapter 13 is remind you of a term we learned either in high school or freshman chemistry called an exothermic reaction. And of course, I failed to point out that when we burn a hydrocarbon fuel with air, that's a very classical exothermic reaction that we engineers in practice really refer to as heat release. And I know that chemical engineers will refer to it as an exothermic reaction. What we're trying to do is generate some type of process whereby we can transfer heat from a high temperature reservoir, that's going to be certainly that flame, into another system, another process. And so our basic combustion question is, and back to my tried and true little gas-fired steam generation unit, gas-fired boiler, how much heat can I deliver to my boiler feed water heater from a known fuel flow, and let's say excess air, to produce steam for my process? And so certainly in your imagination, you can imagine a need for steam, can't you? If you're running a steam power plant, certainly there's that need. Steam can heat other things. In many cases, we run steam through heating coils to heat buildings, commercial grade, industrial grade buildings with very, very large volumes. And on and on and on is a need for steam, for a process. And so the idea is we're going to take a hydrocarbon fuel, for this particular image, a gaseous fuel like methane, natural gas, mix it with some air, little excess air, and then I'm going to try to show you in Chapter 13 how to calculate the amount of heat released as a result of that. In other words, in kilowatts of thermal energy or BTUs per hour of thermal energy. Do you know where we're headed? Well, where we're headed is, now that you've gotten some expertise in writing that combustion reaction equation, a big part of Chapter 13, the next big part and last big part of Chapter 13 is going to be the first law of thermodynamics for combustion reactions. And do you notice here that the sketch I'm showing you as an example, it looks a lot like a gas turbine engine, doesn't it? And notice here what we've got here, little difference. Notice we've got, in terms of mass flows, let's look at mass flows for this steady state, steady flow example. Do you see that we've got air coming in, one inlet? We've got fuel coming in, a second inlet. So you can envision we've got two inlets and one outlet. And also in your mind, you can imagine that in this reacting system where we've got fuel, C sub M, H sub N, and air coming in, do you see that that will be an exothermic reaction by nature of this flame? And I see that the author has, correctly shown Q dot going into the control surface. Now, I might quibble, right, and say the little squiggly Q dot probably should emanate from this flame. That's okay. We can go with that. But anyway, do recognize what we're going to do is we're going to be using the first law of thermodynamics. that you have good experience with already to calculate what's this value of Q dot going to be? Of course, let's start with a sketch. Now, for chapter 13 and most combustion analysis situations, usually this W dot term for some combustion chamber. I know then the textbook calls it a reactor. Let's call it a combustion chamber. Let's call it kind of like the combustion chamber for a gas turbine engine. Do you see that W dot for a combustion chamber, the output power for a mixing chamber that results in flame, results in combustion, W dot is zero. This particular control volume is not lifting a weight. I don't see a shaft coming out of that control volume. So W dot zero. So that's going to simplify our first law. And so our objective is to utilize the first law to determine what is Q dot? What is Q dot for this reacting system combining hydrocarbon fuel with air, getting combustion and releasing heat? So for these calculations, we're going to say we've got an open system. We're operating at steady state, steady flow. What's going on within this combustion chamber is the same at breakfast time as it's going to be at lunchtime. There's no change in kinetic or potential energy of the flowing constituents. Okay. And we're going to say that we're going to dispense with the idea of producing power from this open system itself. From this process, we're not going to have anything to do with power output. We're not lifting a weight. A shaft is not turning at a known torque and speed. And so we're going to go right to write down the first law. This is going to be equation 1315b in your textbook. And notice here, I hope it looks kind of familiar to you rather than just saying, oh, this is a brand new formula. Notice here, left-hand side, it's going to be a heat transfer rate, Q dot, divided by a flow rate, N dot, number of moles per second of the reactants, F, okay, minus W dot. Well, we're gonna throw that away, okay? But complete statement, the first law, steady state, steady flow, W dot over a flow rate equals the sum of the kind of like M dot leaving, H leaving, the products, the combustion products, the mass flow, the mole flow rate leaving times H leaving. There's the dot right there. Minus the sum of what's coming in. We call those the reactants. That's what's going into the control surface. Okay. Mole flow rate in, and there's the dot, times enthalpies. Now, wow. Okay, there's some enthalpy terms here. I'm going to talk a little bit more about on the next slide. But what I'd just like you to see here is how the form of the first law is very similar to what you've already worked with for weeks and weeks and weeks. Left-hand side, Q dot in minus W dot out, all divided by mass flow rates, equals the sum of moles leaving times some enthalpy terms. Enthalpy terms, more of that later, minus the sum of what's coming in, the reactants, times enthalpy, H, terms. Okay, I hope that gives you an idea of where we're headed. The fundamental equation for our combustion reaction, where we're trying to determine the heat generated, okay, is the first law. Okay, now I want to dedicate a slide to what the variables mean. Do you see it? Look at the left-hand side. Now we've thrown away the power term here. How about Q dot over N dot? Do you see how that looks very familiar to you That's kind of like a little Q. I could probably have put a bar over top of that Q to make it mole based, but you get the idea. I want you to just simply get the idea rather than being very precise about this. Q dot divided by flow rate is like little q. Okay. Take a little closer look at these enthalpy terms that are contained within the parentheses for, okay, so this is sum of moles leaving times H terms leaving minus sum of moles of entering in times a group of enthalpy terms in. All right, so now we've got two types of enthalpy terms, H sub F. H sub F, that's called enthalpy of formation. The enthalpy of formation, now that's down at the chemical molecular level, okay? That's what's going to explain the heat release. The enthalpy of formation for the reactants, okay, compared to the enthalpy of formation of the products, okay? So this enthalpy of formation is going to be the source of the heat release, of the amount of heat released as a function of the chemical reaction. So we're not just combining constituents like we did with mixtures. When we combine those constituents, we're getting a chemical molecular reaction. And so for right now, we'll just say these H sub F terms are going to be lookup values. We're going to look those up in the back of the book in a tabular table that tabulates what's called enthalpy of formation. And the units will be kilojoules per kilomole, because I've got this bar over top of the H. Kilojoules per kilomole is what you're going to be looking up in the back of the book for enthalpy of formation, H sub F. Now let's switch gears and look at this delta H. I've got a delta H for both going in terms and going out terms. So I'm subtracting out terms from in terms, but these are actually deltas that you're trying to figure out in order to subtract one from another. This delta H term is called the change in enthalpy above some reference temperature that you, the engineer, set. Okay, so delta H means the enthalpy of the, in this case, exiting enthalpy of all the little constituents going out per mole, kilojoules per kilomole because of the bar, above a reference temperature that you, the engineer, set. Okay, over here, delta H bar of the reactants. That's what's going in. So you've got all your little constituents going in, right? You've got your oxygen going in, your nitrogen going in for your air, as well as, let's say, a gaseous fuel like methane. And this is going to be the enthalpy in kilojoules per kilomole above a reference temperature that you set. So that's a key. And so I've tried to kind of step you through what these first law of thermodynamic terms mean relative to a reacting system, a combustion system. Okay, recap. H sub F, enthalpy of formation. These are numbers, these are values in kilojoules per kilomole that you look up. Okay. These delta H terms, these are enthalpies that are some number in kilojoules per kilomole that are above a reference temperature that you set. Okay, so remember, I've made a point, it's all about the dots, okay? The left-hand side, that's going to be the heat transfer going into the control volume, okay? Now, what do you expect this to be? Q dot N into the control volume. Yeah, I would expect that the Q dot going into the control volume is going to be a positive number. Okay. Enthalpy, and so we've got enthalpies, enthalpy above a reference temperature of the products. We're going to add the sum of the enthalpy of formation of the products. That's what's going out. In other words, the products over here, these two terms here are going to involve CO2, H2O, nitrogen, and when you have excess air, oxygen. Okay. These last two terms, minus what's going in, okay? It's going to be the enthalpy above a reference temperature for the reactants. Well, you've got fuel, oxygen, and nitrogen, okay? And then also minus the enthalpy of formation of these constituents, both fuel, oxygen, and nitrogen. Okay, so I hope that gives you a general idea of where we're going with this. I'm quickly trying to review my the content of my slide here to prompt me on what I want to explain. So left-hand side, heat transfer into the control volume, okay? So you're solving for heat transfer rate divided by fuel molar flow rate. And so the left-hand, so all of these terms, the units of these terms are going to be in kilojoules per kilomole or BTUs per pound mole. This definitely becomes an accounting problem. So it can blow your mind because you have so many terms to deal with. And so notice here the sum term. So you see that you've got to worry about numbers for CO2, H2O, O2, where there's excess air, and nitrogen, because you're burning it with air. So this is an accounting nightmare here. Same thing here on the fuel side. You've got to keep track of enthalpy of formation and enthalpy change and enthalpy of formation for your fuel, for your oxygen, and your nitrogen. So it absolutely becomes an accounting problem, and I would say an accounting nightmare. Lots of constituents and values to keep up with, okay? You, the engineer, have to select a reference temperature. Now, this is a little easier than it appears. You're going to typically select, if you're in English units, you're going to be selecting 537 degrees R, which is a standard temperature in the combustion world that you would select. I believe that's 77 degrees F, right? So that's sort of a standard for combustion problems. And over here, notice here in metric, you're going to select 298 degrees K as your reference temperature. Let's see, what is that? That is 25 degrees C, which is very standard reference temperature to pick for SI problems related to combustion. Okay, so three things. You're solving for all of the units in this first law expression are going to be in terms of kilojoules per kilomole or BTUs per pound mole. It's an accounting nightmare. Lots of constituents and values to look up and deal with, and typically you're going to select the reference temperature. So rather than doing an example problem that would take a long time, I did a number of homework problems. And so what came to me was, gosh, I could create for myself in Excel a calculation tool where if I make it generic enough, I could have a tool on hand where I enter what I need to enter. In other words, C sub M, H sub N. If I enter the number M and I enter the number N, and I can enter the number of excess air that I have, the percent of excess air, I could make a generic calculation tool that gives me the result over and over again without having to do a lot of repetitive work, as long as I can create a tool that does this one single time accurately. And I want to offer this Excel tool to you. You can download this Excel tool that does this work for you. And I'm going to go live here in just a second, but I'm going to try to show you to go to Jay's Toolbox website. This is going to be jaystoolbox.vt.domains. And this will be the front screen. You're going to scroll, you're going to go to Toolbox, drop down the Toolbox menu, go to Excel Docs, XLS Docs, and drop down XLS Thermal Systems. And if you can drop down that menu, you can scroll down, and depending on your problem, whether you're an English or SI, that's so complex, I can't build it all into one single file. You can download one or the other of these files, and you can run my combustion model and get some numerical results. And you can see with your eyes what are the numbers and how do they all fit together. I've done my best to make it simple looking so that you can see how all of this fits together. So I've got a note here to go live. So I'm going to try to do that. I'm going to try to get out of PowerPoint. Looks like I'm out of PowerPoint. I'm going to go to my website. I'm in my browser, and I've looked, okay, here I am at my website, jaystoolbox.vt.domains, and I'm going to scroll down a little bit to drop down Toolbox. I'm going to come down here to XLS Docs. I need to scroll down a little more. XLS Docs, and then come over here to Thermal Systems. I'm going to click Thermal Systems. Okay, it takes me to a new page. These are all the Excel files associated with thermal systems that I offer to anybody to download. I'm going to scroll down, and here they are. All you have to do is click the download button if you have an English system problem, or click the download button if you have an SI units problem. Click those. You can download the Excel file, and then you can possess it. There's no passwords. There's no special restrictions. It is simply an Excel file that I've created for myself and to share with anyone else who's interested to do a basic combustion calculation, similar to homework problems you would have on your homeworks. Let's go back to PowerPoint and talk about that a little bit. Back to PowerPoint. I'd like to show you the general idea of what my Excel file that you will have downloaded looks like. So there it is up at the top. It's called, the title page is called Combustion Reaction Calculator. Notice here the restrictions: open system, steady state, steady flow, complete combustion. In other words, no carbon monoxide in the exhaust. But I do want to remind you that you may be able to solve one or some of your homework problems with my tool. It would definitely be a violation of the honor code to simply turn a paper copy of my tool results in as your work, right? That wouldn't make any, that'd be a violation of the honor code. Don't do that, okay? However, I provide this to you so that you could at least have some numbers in front of your face to sort of check your own work as you go along in solving your problem. So here's the basic steps that you would take to run this Excel file, and the same basic steps you would take to solve this problem on your own as if you did not possess this Excel file. So let's look at the basic steps. Step one, define the values M and N in your fuel. So if you had, of course, if you had methane, M would be 1, N would be 4. If you had propane, M would be 3, and H would be 8. Enter the percent theoretical air. In other words, 10% excess air would be 110% theoretical air. You're going to enter that number, or decide on that number. You're going to go and select the available fuel. So this would be similar to you're going to the back of the book and looking up numbers in the back of the book for your fuel. You'll select pertinent temperature. So for example, you will set the reference temperature at one or the other of these values. You're going to have to know what is the fuel and air inlet temperature. That would be given in a homework problem, or in a real world problem, you would know the inlet temperature of the fuel in the air. It might not be at the reference temperature. It might be at the reference temperature, but you need to know that. The exhaust temperature of the product. Now that's going to be very important. In many cases, in most cases, you're going to know that temperature and it is going to be hot. The exhaust temperature of combustion is going to be a high number, well over 1,000 degrees R, well over 1,000 degrees C. And what's the objective? The objective is to go through that first law of thermodynamics, an accounting nightmare, and determine the computational result, which is the heat produced per kilomole of fuel. In other words, little q bar. The result will be kilojoules per kilomole or BTUs per pound mole. So just some screenshots of my tool, right? So in the screenshot of my tool, here's define the hydrocarbon fuel model. Those two yellow cells, you're going to fat finger in two numbers. In this demo, I've got methane CH4. The next thing you're going to put in is the theoretical air fraction. For this case, I'm using a huge amount of theoretical air, 365% theoretical air. So if you have a stoichiometric mixture, you'd put in the number 1.0. If you had 10% excess air, you'd put in 1.10. Okay, so like in this middle example, you put in 1.10 for 110% theoretical air, which is the same thing as saying 10% excess air. So that's how I know this 3.65 is a huge number of excess air. This would be kind of like a bonfire or a fire pit using natural gas as its source. The next thing you do in my tool is there's a drop-down box, a yellow drop-down box where you select the fuel. And so I have coded in Excel all of the fuels that are available in the back of the book. And so you can see here's a little pick list of what you have available to you. And I've picked methane as my little example. And so I am looking up the enthalpy of formation of methane, and it's negative 32,210 BTUs per pound mole. Okay. And also I'm looking up enthalpies of formation for CO2 and H2O. That's going to be in the products side. So enthalpy of formation are lookup values in the back of the book. The next thing is you specify the reference temperature. And since my little example problem on the screen here is English, I've set 537 as my reference temperature. Well, once you have those, you have the enthalpy of the reference temperatures. These are the enthalpies of the reference temperatures. You go in and select the temperature of the products. And again, these are lookup values in the back of the book. So you can find those, the temperature of the products. And let's see, CO2, that's going to be a familiar ideal gas table in the back of the book, okay, that you used after the air tables. Ideal gas, CO2 is an ideal gas. So it's a lookup value at the temperature of the products. Okay, carbon monoxide, we don't need that. We're not going to use that, but I look it up anyway. H2O, O2, and nitrogen. All those are H bar values looked up in the back of the book at 700 degrees R. I think that's going to be table A24. Now, this table then, so that's enough to do all of the computations. And I'm trying to, in this, my automated tool, I'm trying to show the way that computation flows in a somewhat understandable format. So notice here, I've got my products, okay? That's going to be these top two tables. And the reactants, so that's the exhaust gas table. The bottom set of tables are the reactants. That's the fuel and the air, okay? And so I've had to go in and on the automated tool, it's so easy. It's a matter of going in and matching up rows with what you've selected in terms of temperatures and fuels. So it's child's play for looking it up in Excel. Very difficult if you're doing it by hand, but this is the little demo so you can check your work against a working generic tool. And so I've tried to show, so notice here in my tool, I've made a screenshot of the first law. Little qn equals 4 basic big terms. So notice here, okay, so let's look at this term, this left term here. That's this box right here. So do you see, this whole box of numbers simply is designed to get you this one number. 41,457 is this term here, okay? Next term, that's going to be this box over here, okay? NEHFE bar, okay? Et cetera, okay? So these are the enthalpy of formation over here. This box is the enthalpy above the reference temperature. And then the reactants, same idea here. This box, NIHFI, that's this last term. This middle term is this. And so do you see what I'm driving at? You see how I said it's an accounting nightmare? And it is. And so these numbers, these final numbers here are what's giving you the numerical result. So it's just an absolute accounting nightmare, okay? And so in this case, the number is negative 309,286. In other words, for the combustion process, negative 309 BTUs per mole are added to the combustion process, which means 309,286 BTUs per mole are being added, released into the open system. So you want to expect a negative number for this numerical result for the combustion process. That means the flip of that, 309,000 BTUs per mole are being released into the open system. Okay, and so there you go. So understand is the heat transfer is going into the open system. The negative sign says, the negative numerical sign says that heat is rejected from the open system into the lower temperature substance. Okay, that's the idea. So that's the idea here, is that you're wanting to transfer heat from hot to a less hot environment. And so don't be nervous when you get a negative value for Q in to the reaction. So this is an exothermic reaction. Exothermic reaction. So expect to get a negative number for heat into the reaction. Talk a little bit more about the generic tool that I'm trying to offer you, get you some interest in some limitations of that Excel automated tool. The temperature selections are only from a drop-down pick list. So if you're given some odd temperature that doesn't correspond to that table A24 temperature pick list, all bets are off. I can't do the interpolation in between those numbers. can interpolate between the pick list temperatures. The reactants, in other words, the fuel and the air going into the combustion chamber, are at the same temperature. I don't allow for the fuel being at a different temperature than the air. The combustion air is considered to be dry. In other words, we're only dealing with dry air, not air with a certain relative humidity where you'd have the extra effect of H2O vapor in the air starting. Of course, we all recognize that H2O is a natural exhaust product of hydrocarbon fuel production, combustion. This tool only applies to C sub M, H sub N fuels. Now you can put any real number in for M and N, but it doesn't address the moisture content of fuel like wood chips. This model is for complete combustion, and so I don't do anything in my tool to allow for carbon monoxide in the exhaust. Okay, so the takeaway of this full combustion analysis where we determine numerically what is the heat released from a hydrocarbon and air combustion situation. It's a complex first law analysis, steady state, steady flow, open system. No work is involved. The first step is writing down the first law with those complexities we talked about. And the key to success here is keeping close track of units and the forms of energy in terms of enthalpy of formation, enthalpy above a reference temperature, and those type of accounting details. So I'll have to openly admit that it's a frustrating and time-consuming study in accounting and energy balance, balancing heat release with enthalpy of formation and enthalpy change. Now, believe it or not, that was a high-level overview of your introduction to combustion. It gets much more advanced at the graduate level. I'm going to have to say that I only scratched the surface in my industrial experience looking at combustion analysis. Typically, in my experience, I used what's called I used a lookup table to determine the heating value of fuel. That was the word I was searching for, the heating value of fuel. And that's what's going to be contained in the next and last module, is really looking up the effective heating value of fuels. It gives you a general feel for calculations. It doesn't give you this detailed look at it, but at least it gets you going as an engineer. So I hope this somewhat complex module helps you get started if you are assigned one of these detailed heat release computations in Chapter 13. Check out, download that combustion reaction equation automated tool, and I'm hoping that'll help you, give you some guidance in where to go in your own manual calculations.